Electric power is everywhere present in unlimited quantities and can drive the world's machinery without the need of coal, oil, gas, or any other fuel. This new power for the driving of the world's machinery will be derived from the energy which operates the universe, the cosmic energy.
These are the words of Nikola Tesla. The man with his belief and his knowledge was able to change the world. But how? First, Tesla arrived in the United States by a ship. Shortly after his arrival, he became a student of Thomas Edison. The man was known for his invention of direct current power. And his idea of direct current power was to have the generator in every block or two of neighborhoods. But his invention had a serious problem. Direct current power generators were weak and broke all the time. Thomas Edison took this problem to his new student, Nikola Tesla, and decided to give him a challenge to fix this generator that no one else could fix. And he will give him a reward of $50,000. Tesla was able to complete this challenge successfully, but in the end, he was betrayed by Edison. So now, we have this famous conflict between Tesla and Edison. Tesla managed to invent alternative current power in his own, which is still used in American homes today, but Edison tried his best to stop Tesla from succeeding.
So I'm going to be walking you through the circuit we've designed. We start with our power source and connect that to the first spindle of copper magnetic wire. And for the second circuit, we're going to have our light bulb functioning as a resistor, and that will be connected to the second spindle of copper. This shape may look familiar because this is how transformers work, but instead of having an iron core, we just have air. Wireless power transfer requires an alternating current. To help visualize this, we have paper and a towel. Direct current would be represented by a singular motion, on, off. Notice how the paper doesn't move. Alternating current is represented by moving the towel up and down really fast. As you can see, this generates current moving the paper.
In this project, we have done 3 experiments. For our first experiment, we are working with a regular copper wire that we bought from Amazon, not realizing that making a coil would cause the wire to touch itself, causing a short out in the circuit. For our second experiment, we come up with another wire that had a plastic insulator. As you can see, the coil is working, and we got a reading from the multimeter of 5 mV when coils are on top of each other. But the problem here was that the power is very weak due to the large insulator. This power was not enough to light the lid. For our third experiment, we have a magnetic wire. The difference between magnetic wire and regular copper wire is that magnetic wire have a very large insulator that prevent a short out.
So that's the main thing. Going from 0.16 millivolts to 0.52 millivolts. Let's see what frequency does to this. All. Oh my God, are you seeing this?
Yeah. 1 volt. It's on. It's on.
Oh,
No way. Oh, let's go.
It's possible that many of you are already familiar with wireless charging. Toothbrushes have used inductive charging since the 90s and phones since 2013. To help you connect the dots, we've pulled apart a wireless phone charger. As you can see, there are copper coils, just like in our experiment. There is another copper coil in every phone capable of wireless charging.
So now I'd like to talk a little bit about an observation we had during our testing. So we had noticed that at some frequencies, our light bulb would be an on-off sort of reaction, and at other frequencies, we'd have gradual, where as we brought the light bulb, it would get brighter and brighter, and as we brought it away, it would get dimmer. And I would like to show you a demonstration of something that we can visualize to interpret why is this happening. So this is an interesting demonstration of how we can relate high frequency and low frequency to an on-off versus gradual switch. So when we have low frequency, we can imagine that this is our on position, and as soon as we release it and move it away, it now snaps to its off position. Whereas if we have high frequency and we turn it to our on position, it more gradually returns to our start instead of a very fast snap. Tesla is planning on using wireless charging in their new Cybercab. This would allow the Cybercab to pull into a station, charge up, without needing to be plugged in by a person.
What does charging look like in the future? Imagine walking into a room and your phone automatically begins charging.
Another future example of wireless charging technology is shown in this video by Huawei. They have a central power box that charges a phone, lights, blinds, fan, and even a TV just by being in the same room. This is a great demonstration of how resonance can increase the distance between an item being charged and the power source. But how does resonance help increase the distance? If the frequency of the power box and the item being charged is matched, then the distance between the two can be greatly increased. A more intuitive understanding of resonance can help explain why this happens. So now I would like to do a visual demonstration between resonance and non-resonance in regards to a circuit. So we have this water bottle attached to an elastic band, and in a resonance circuit, my hand is working with the water bottle to optimize the mass transfer, or in the case of a circuit, the power transfer. Versus in a non-resonant circuit, the hand and the water bottle are not working together and can cause uneven distributions of the mass.